Well, thank you very much. In the time allotted to me, I want to try and tell you something about the modern picture of the universe and place some emphasis upon the thematic words in the title of this week's proceedings, special moments, so rather unusual and special times in the history of the universe and in its future, and also the idea of extremity, of particularity, of specialness. Well, in the end of the 1920s, the greatest discovery of 20th century science was made, to my mind, when astronomers first discovered that the universe, everything there is, in a state of overall expansion. For thousands of years, astronomers and philosophers and scientists had thought that the universe of space was rather like this dance floor of stage in front of us. It was absolutely fixed and rigid, and upon it were played out the movements of the planets and the stars and other celestial bodies. And they moved in accord to rules that we called the laws of nature. But however things moved and however the play developed, nothing could change the fabric of space. Nothing could alter the rate of flow of time. But Einstein's theories of special and general relativity, which culminated in 1915, removed that ancient prejudice. General relativity still remains the most sophisticated physical theory that we have, because it doesn't only provide the rules about how particles and radiation moves around and how it interacts, but when it does so, it changes the nature of the geometry of space and the rate of flow of time in the space-time in which the interactions take place. A consequence of all this, which was really appreciated not fully by Einstein but by others in the years soon afterwards, was that the whole universe was in a state of overall dynamic change. And in the late 1920s, astronomers discovered that that state of dynamic change was one of so-called expansion, discovery made primarily by Hubble and by Hummerson. So this picture of the expanding universe, which we've occasionally had allusion to in other presentations this week, is an odd idea once you start to think about it. I mean, what's expanding? You're not expanding, the Earth's not expanding, the solar system isn't expanding, our galaxy of 100 billion stars is not expanding. So what's expanding? If you keep going, you will eventually come to great clusters of galaxies with hundreds of thousands of members. And these are the objects that are marking and tracing the expansion of the universe. Things that are on smaller scales, like galaxies and solar systems, are held together by stronger gravitational forces that exist locally. You and I are held together by chemical forces, which are much stronger than the effect of the expansion of the universe over our dimension. The image that's sometimes given, that Eddington and others introduced, of having a huge lump of dough in the oven with raisins in, you put it in the oven, the dough starts to rise and expand. The raisins do not. They move apart. They're held together by rather stronger forces than the raising temperature can liberate. And the space in between the raisins increases as the dough rises. Well, this expansion of the universe, to many people, the first question you get asked about it is, what's it expanding into? Or, does that mean we're the center of the universe? Because if everything's expanding away from us, doesn't that mean we're at the center? Or where did the expansion begin? So these questions are really not appropriate ones. They derive from a more local intuition. The expansion of the universe is not an explosion. The universe is not expanding into anything. It's everything that there is. And there is no preferred point from which the expansion emanates. So you wonder, well, how can this be? And there are two types of situation that you have to envisage. The easy one is if the universe is infinite. And this was a challenging idea. People used to get burnt at the stake as late as 1600 in Rome for promulgating the idea that the universe was infinite. And why was it a dangerous idea? Well, here is a picture, an engraving by Escher, a beautiful piece of craftsmanship, and it attempts to convey the idea of a never-ending space threaded by a network of girders. And if you locate yourself here and look around you, you will get exactly the same overall impression that if you look around from here, or here, or here. So we say the universe is the same in every direction. It's isotropic. It's the same on the average from place to place. It's homogeneous. Now suppose we raise the temperature of these girders. They will expand. And these distances in between will increase. And if you stand here, you will see all the other crossover lumps moving away from you as though you are at the center of the expansion. But you will see the same thing if you sit here or you stand here. So every point in this space behaves as though it's at the center of the expansion. And of course there's no edge because it's infinite, boundless, endless. This feature of every point behaving as though it's the center is why this was such a dangerous medieval idea. If you're promoting the thoughts of Aristotle, then having a finite universe that has a preferred single center, a preferred place, that had become part of the doctrine of the Judeo-Christian Aristotelian synthesis. So in such a universe there could be a special center, and that was where the earth was supposed to be, in a privileged and special place. In an infinite universe there was no such place. And so this was not an idea that people liked to receive. If you went to the presentation up at the observatory last night, you will have seen a dynamic representation of this famous Eddington picture of the expanding universe as a ball. Why this is interesting is the last example I've given you is why it's reasonable to see that an infinite universe has no edge and it has no center to its expansion. But for a finite universe, this seems an impossible idea. If I hold up this two-dimensional universe, this flat sheet of paper, it's finite. How could it possibly be that it doesn't have a center and it doesn't have an edge? Have you ever seen a finite piece of paper that doesn't have a center or an edge? And if it's flat, like this piece of paper, that is indeed impossible. But if it's curved, so the two-dimensional surface is like the surface of a ball or a balloon, then you can see it is possible for this surface to be curved and for you to walk around upon it if you're an ant and never fall off the edge. So it is finite, but it has no boundary. If you were to inflate the balloon so that it gets larger and larger, as we saw demonstrated last night, if we were to mark points on the balloon, they move away from one another steadily as the balloon is inflated. And wherever you located yourself on this balloon and looked around you, you would have the same experience that you had in Escher's picture. You would see all the other pictures of galaxies moving away from you as though you were at the center. And that will be true no matter where you located yourself. The real center of the expansion doesn't lie on the surface of the balloon in the space of the two-dimensional universe. It lies in a third dimension, as it were. So if our universal space is curved, it is as though it is the surface of an expanding four-dimensional ball, perhaps imaginary ball. So these are some simple lessons about how one should view the expansion of the universe. Not quite as intuitive as one might have imagined. The idea of the expanding universe, this picture that the universe was once smaller and denser and hotter than it is today, has become known actually as the Big Bang theory, almost irrespective of whether it began with a bang or not. So the Big Bang label is reserved for universes that are imagined to have a hot, dense past And as time goes on, they get cooler and sparser. So here is a little cartoon picture, as it were, which we'll show one or two times. Here is time in billions of years. So cosmologists tend to think in different units of time when they're talking about different epochs in the history of the universe. Here is some measure of the amount of expansion that there has been, separation between some distant points, and here is the trajectory of the expansion, things getting larger and more expanded. And we live about here, about 13.7, 13.8 billion years after the apparent beginning. So that's the first weird thing about this scenario. It implies that if you asked a question like, what was the universe like 20 billion years ago? It might not have an answer, because there might not have been any universe 20 billion years ago. So a key question is to understand what's going on here, if anything's going on. But the real issue, the real new ingredient that the idea of the expanding universe brought was twofold. First, to become familiar with talking about enormous periods of time. Not just millions of years, but many, many billions of years. Weirdly, although the universe as a whole appears to be about 13.7 or so billion years old, we'll call it 14, you can walk around in the north of Scandinavia and pick up rocks that are nearly 4 billion years old. So the apparent beginning of everything is not vastly removed in time from the age of quite mundane objects and rocks that you can pick up and see. What this expansion really does for you is it creates a picture of what you might call a developing or evolving universe. As the universe expands, the temperature changes, the density of particles changes, the identity of prevalent populations of particles also changes. And there are periods during the evolution when it becomes possible for life of any sort to exist. And so there is a story, as it were, about the evolution of the universe. Today the universe is very cold, it's very cool, the temperature is just 2 or 3 degrees above absolute zero on the average radiation. If we were to go back to when the universe is 1,000 times more contracted, it will be 1,000 times hotter, 3,000 degrees. There could be no atoms, no molecules, no life, no planets, no stars. The universe is a much simpler and, no doubt, less interesting place. So as you move forward from this time, about 250,000 years after the apparent beginning, things cool off, simple atoms can form, simple molecules, and then some parts of the universe that have been expanding just a little bit more slowly than the average, because they've got more stuff in them to exercise more gravitational restraint and pull, they start to attract material and they become so restrained in their expansion that eventually they stop expanding altogether and turn around and condense and collapse to form great clusters of galaxies of the sort we see today. And within them form the galaxies, and within them the stars, and ultimately the planets that we observe in great profusion. So there's an unfolding story of structure developing, and on our own planet we know some processes of biochemistry, the origin of life in different forms appeared. And we don't yet know whether this is a generic phenomenon, whether we will expect to find similar or different forms of life on the many, many other planets which we've now observed around other stars. In the future, the long-range forecast is rather bleak. As we heard the other evening, eventually the sun will exhaust its fuel, it will explode, it will collapse at its center. Other stars, according to how big or small they are, will suffer maybe the same, maybe different, but equally uninviting fates. And the universe seems to be becoming a great cosmic cemetery. of dead stars, dead structures of all sorts, and ultimately there will be no possibility for processing information, what we would consider an essential ingredient of life. So there is an interval in cosmic history after the stars form, but before all the stars die, where if you want to evolve life for the first time, you must do it in this interval. Once you've done it for the first time, it might help the evolution of life elsewhere. So not surprisingly, we sit within this habitable zone in the evolution of the universe. And this biases many of the perspectives that we have on the universe. So this is our first sort of special, if not moment, then interval of time. And if we focus upon this, we can see what it does for us. We might ask a question: why is the universe so old? Talking about 14 billion years old, is there some reason why we should not be surprised by this? Could we have found a universe that was thousands of years old, or we found it to be millions of years old? Well, there's an interesting answer to this question. Life and the ingredients of life, atoms like carbon and oxygen and nitrogen, the components of us and of the various birds that we have seen on different days during this meeting, they're made of these biologically fruitful elements that can undergo all sorts of gymnastic interactions with themselves and with other elements. And these elements, like carbon and oxygen, don't appear spontaneously in the universe at its beginning. They're made in the stars by a long process of nuclear reactions. And these reactions take billions of years to complete. A simple part of the network would be for 2 helium nuclei, 2 protons and 2 neutrons in each nucleus, to combine to make beryllium. And then for helium to combine with beryllium again to make carbon. And this reaction is responsible for all the carbon in the universe, all those carbon nuclei in your body, the fruits of this interaction, and the explosive end to the star, which will spread the contents around the universe. It may be that your carbon atom went back through a star again and went through this process a second time before it came to you. Remarkable coincidences in physics make this interaction possible. It's a sort of hole-in-one that requires very, very special conditions. There just happens to be an energy level in the carbon nucleus with an energy almost exactly equal to the combined energy of beryllium and helium. So this interaction is like a hole-in-one. It goes very easily, like swinging on the swing. When you give a push at the right moment, you create a resonance. So here, this is a resonant nuclear reaction. This reaction just fails to be resonant. Were it resonant, all the carbon would disappear off into oxygen. It's rather more explosive. So the key point here is that these crucial interactions to produce biologically interesting elements take billions of years to complete. And so we shouldn't be surprised to find that the universe is so old. If the universe was significantly younger, it wouldn't contain the building blocks of any complexity, atomic, molecular complexity of any sort. So the universe would have to be pretty much as big as it is, even if we were the only outpost of life in the universe. Suppose you wanted a universe to be rather smaller than ours. I'd ask this question: why is the universe so big? It seems awfully impersonal. If we were in any sense a goal or a special feature of the universe, couldn't you have got away with a more economy-sized universe, a little bit smaller? But the fact of the expansion means that the size is inextricably bound up with the age. Because you need many billions of years of time to make the building blocks of life, you need many billions of light years in size to accompany that. If the universe was just the size of our Milky Way galaxy, There will be 100 billion stars there to evolve life, but it will be little more than a month old. So hardly enough time to pay off your credit card bill, let alone evolve complexity of life. So the huge expanse of the universe is not quite as impersonal and totally unrelated to us and the conditions necessary for our existence. We could not exist in a universe that was significantly smaller. The other odd thing about the universe is that to a first approximation, it doesn't contain anything at all. It's just empty space. I mean, all the material in it is a tiny drop in this huge expanse of space. This picture here is the so-called Hubble Deep Field, a famous image which was taken by the director of the Hubble Space Telescope many years ago, Williams, just pointing the telescope in one direction for about 30 days and just taking a deeper and deeper image of this area. Almost everything that you can see in this picture, which is not very high resolution here, is itself a galaxy containing about 100 billion stars. The whole image would just be at your thumbnail at arm's length. So it's a tiny, tiny piece of the whole universe. Most people are excited by the little flashes of light. There's a barred spiral galaxy, an elliptical galaxy, it looks like an interacting galaxy. But a big puzzle about this picture, in many ways, is the dark space in between, as we'll see in a moment. So how empty is the universe? Well, on average, if you take ordinary stuff that we're made out of, atoms and molecules, there's roughly about an atom, one atom in every cubic meter of space, if you smooth everything in the universe out into a sort of uniform distribution of equally spaced atoms. You couldn't make any vacuum in any laboratory on Earth that was as empty as that. So that's why I say, to a first approximation, the universe doesn't contain anything. It's just empty. If you start to gather the atoms together a bit more realistic, into planets like the Earth, then this density corresponds to running into a planet every time you go about 10 light years. And it corresponds to meeting a star like the Sun every 1,000 light years. A light year's a long way, okay, 186,000 miles per hour, okay, over a year, 10 to the 7 seconds. If you gathered the stars into galaxies of 100 billion stars, you'll be going 10 million light years before you ran into another galaxy. So the sparseness of the universe, the huge distance to our next star system, is a reflection of how little material there is in the universe. So it's no accident that extraterrestrials are a rather long way away. The other feature of a universe that's big like this, and the large size, you remember, is a consequence of the large age, the huge amount of expansion. This ensures that things become really rather low density, and the volume in which everything is contained is always increasing. If you expand a ball of gas, then the temperature, the average speed of the material inside, will drop. So as I always used to tell our children, the universe is cool, very cool. And this is another consequence of the huge amount of expansion that's gone on. So just about 3 degrees above absolute zero. And here's this picture again, with all the dark space in between stars and galaxies. So what's odd about this is really an echo of a question that was first asked over 300 years ago by Edmund Halley. Why is the sky dark at night? So it sounds a sort of obvious question. You know, somebody needs to get out more. Okay. What an odd question to ask. But what Halley was thinking, he was wondering, you know, back in the day of Newton, whether there could be an infinity of space as well. And he was puzzled by the fact that if you stood in the forest, for example, and you looked out into the trees, then everywhere your line of sight ends on the trunk of a tree. So that in front of you, you see a great line of tree trunks. You can't see very far. And so he wondered, why wasn't it the same when he looked with his telescope out into space? Why doesn't your line of sight everywhere end on the surface of a star, so that the whole of the sky all the time looks like the surface of the sun? And if there was an infinite number of stars, as he was imagining, this must happen. So why is the sky dark at night? Well, this is a question that was really only answered in the 20th century with the discovery of the expanding universe. This very low density of material in the universe is the key. If we were to turn all the matter in the universe into radiation light, just like that, there is so little matter in the universe that the effect on the brightness of the sky would be imperceptible. The temperature would rise from 3 degrees above absolute zero to about 50 degrees above absolute zero. There's not enough energy in the universe to illuminate the sky. And that's a consequence of the expansion, which has been steadily reducing the density and the temperature and the luminosity. But if you went back in time to when the universe was 1,000 times more contracted than today, when it was 250,000 years old, the temperature, you remember, was 3,000 degrees. And that's when the whole sky was bright. But there could be no observers then, no atoms, no molecules. So there was a bright sky, but it was in the dim and distant past when the universe had no structure in it. But today, the density, because of the great age and the great size, is too low to sustain a bright sky. Well, these insights that you get from thinking about the expansion of the universe give you a picture of the universe, a sort of philosophical reflection on it, that really turns upon its head the type of rationalistic view that was common in the first third or so of the 20th century. So if you look at someone like Bertrand Russell, for example, he feels that the emptiness and vastness of space means that somehow life and observers are sort of anathema to the nature of the universe. But what astronomy has taught us is that these curious features of the universe, that it's almost empty, that it's big, that it's old, that it's dark, that it's cold, these are all necessary features of a universe that's going to be able to produce and sustain complexity of any sort, including the sort that forms you and me. So these are not properties of the universe that should be regarded as somehow alien and contrary to a force of life. Well, let's move on and look back towards the beginning of the universe. So universes, we've just talked about the expansion of the universe, but universes are rather like your financial investments. You know, as they all say on the bottom, you know, your investments may go up, but they may also go down. If you're invested in China, you'll find that they can also plummet as a third option. But expanding universes are rather like this. They may expand and keep on expanding forever, apparently, or they might one day reach a maximum and then reverse into a state of contraction, heading to some apparent big crunch at a finite time in the future. And in between, there's a sort of British compromise universe that just manages to make it all the way to infinity. Many, many years ago, I was invited to go and give a talk to Mrs. Thatcher and some members of her cabinet about cosmology. So every so often, she would ask some young scientists, as we were at the time, to come and tell her about some area of science, just as entertainment, because she didn't like to go to the theatre or the opera or anything like that. So her idea of a very interesting day was to have some people come and tell her about things. And so the day before, I had to report at the Cabinet Office while they were putting the bulletproof glass in the room, and sort of talk for 5 minutes so her special advisors could say whether this sounded the right sort of thing to be telling the Prime Minister about. I think I showed a picture not dissimilar to this because I was talking about dark matter detection. And I said, and then there is this British compromise universe and so on. And the advisor said, that's fine, no need to go on, we think everything will be all right. And he said, but can I give you one piece of advice? He said, when you mention that British universe, try to be much more upbeat. It's just the sort of thing the Prime Minister likes to hear about. So it was good to know the country was in such good hands. But if you're a cosmologist, one of the things that you're trying to do is to reconstruct the past history of the universe back in time as far as you can go. And to do it by making some predictions as to what you should see today, if you tinker with what you think things were like there, but also to find some fossil remnants from things that might have happened long ago that you could see today. And the greatest of these remnants was discovered 50 years ago, with a month to spare. And it was the discovery of the heat radiation left over from that hot, dense, early beginning. So this was really the time when this so-called Big Bang picture of the universe really became the key paradigm. And this picture here is a measure of intensity and brightness, and here's frequency. And this is the so-called Planck pure heat spectrum, the solid tube to guide your eye here. And this spectrum, about 2.7 degrees above absolute zero, measured now from space, many occasions, is the most perfect example of a heat spectrum ever found in nature. So the accuracy to which this is a heat spectrum, parts in 100,000. Those circles are just to guide your eye, they're not the error bars. The error bars, if we could draw them, would be 500 times thinner than the thinnest line we could draw on the picture. So the universe has given us this perfect example of heat radiation left over in relic form from its first moments. If you've got an old-fashioned television, you can still observe this. So if you don't have sort of fancy sort of cable things, you have an old-fashioned television and you detune it a bit so you get all this sort of white snow on the screen. Just a few percent, 3 or 4% of that snow is this background radiation from the beginning of the universe. So good are radio receivers today. Well, the discovery of this radiation very soon led to people wanting to know if it had the same temperature in different directions. And for peculiar reasons that I won't go into, you can actually measure the differences between the temperatures in different directions thousands of times more accurately than you can actually measure the temperature. And it was soon discovered that this temperature was the same to better than 1 part in 1,000 in every direction. Big puzzle. So we now know it's the same to an accuracy of 2 parts in 100,000 in every direction. So that means that the universe is expanding at the same rate in every direction to this extraordinary precision. Big mystery. The 1970s, at the beginning of the 1980s, great deal of effort in order to try and understand this. Why is the universe expanding like a perfectly spherical ball? And also, equally puzzling, why was it expanding to within a couple of percent or so close to this critical expansion divide? You can see from this picture that it has the property, what scientists call it's unstable. So if you start a little bit different to the critical divide, you'll either run away up here, or you'll peel off here and collapse. So we are extraordinarily close to the critical divide, even after 14 billion years of expansion. And this means that the initial starting speed, if you like, the expansion, must have been fantastically fine-tuned to remain close to that divide for 14 billion years. So again, this is a mystery. It was a mystery until about 1980. The other weird thing about the universe, we said it's expanding at the same rate in every direction and it's going close to this critical expansion. If it was going much faster, the critical expansion, or much slower, either it would have gone too fast for any galaxies and stars to form and we wouldn't be here, Or it would have hit a big crunch before the galaxies and stars form, and we also wouldn't be here. So being close to that critical divide is another one of these features that's rather important if there's ever going to be any us, or any them, somewhere else. But in order to have stars and planets and galaxies, you mustn't have a universe that's perfectly symmetrical and smooth. There must be some little variations in the density. And on the average across the whole universe, there's a pretty constant average graininess to the universe. And it's about 1 part in 100,000. And that's the level of the little differences in the temperature of the radiation around the sky that reflect this. So the universe is not perfectly symmetrical. It has this little graininess. So why is it 1 in 10 to the 5? You know, if it was 1 in 10 to the 6, again, there wouldn't be any galaxies and stars. It wouldn't be grainy enough to make them. If it was 1 in 10 to the 4, they would have all formed dense lumps and black holes, and we probably wouldn't be here either. So again, it's rather important for us that this special number emerges. So the sort of thing that cosmologists spend their time doing, or did from the 1980s onward, was trying to explain these 3 unusual features of the universe. And rather fortuitously, Alan Guth, an American particle physicist, came up with a proposal which solved all these problems at one go. And it's known as the inflationary universe theory, and it has all sorts of different versions and how it would emerge from particle physics theory. But at root, it's a very simple idea. And if you watched closely when we drew this picture before, the size against time, you might have noticed that all the trajectories sort of curved over in this direction. Okay, whether they were going to go to a big crunch or whether they kept going forever, they all curved over in that direction. Geometrically, it shows you that the universe is decelerating once it starts expanding. Because the only force acting on it is the gravitational pull of one of the constituents on all the others. And gravity attracts and decelerates. Guth's idea at root is that there was a tiny interval of time near the beginning of the expansion when the expansion accelerated and then reverted to its old course of deceleration at the end of this tiny instant of time. This wasn't an entirely unmotivated idea. There were types of matter being explored in the theories of particle physics at that time, types of matter which are now recently discovered to exist at CERN, the Higgs boson, which could contribute this type of repulsive gravitational effect. They're types of matter which behave repulsively one upon another under the influence of gravity. And these particles are likely to be unstable, so they come into play here, they create this acceleration, and then they decay away into ordinary particles and radiation which don't have that effect. So this is roughly the scenario, and this tiny interlude of acceleration has all sorts of remarkable consequences. First of all, once it begins, then no matter how directionally different the expansion, no matter how anisotropic, all the differences very quickly get removed. So the expansion in every direction quickly proceeds to the same rate and becomes isotropic. So no matter how the universe begins, it ends up here expanding very isotropically. The other thing that you can see from this picture is the effect of this acceleration is, by this time, the universe has become much bigger, much more expanded than it would have done if it had followed that trajectory. And what that does is to push the expansion close to that critical divide for very, very long periods of time. So this is happening exponentially quickly, and so you can explain again, fairly convincingly, that however you began beforehand, you would expect to be extraordinarily close to that critical divide 14 billion years later, so long as this period of inflation lasted long enough. And long enough here means from 10 to the minus 35 a second to 10 to the minus 33 a second. It's a mere blip in the history of the universe. Here's the same picture in a different sort of cartoon model. So we sit here today, and as we look around us, there is something that we call the visible universe. So this is not the entire universe, but it's the whole part of the universe that we could in principle see with perfect telescopes. And it's roughly equal to the speed of light times the age of the universe. Not exactly, because of the expansion. So there's no doubt lots more universe beyond that horizon of 14 billion light years, roughly. But we can't see it yet. Tomorrow, with a perfect telescope, we could see one light day further. And so we're interested in knowing why one side of this visible universe looks the same as the other side, why it's got little fluctuations in it at the level of 1 part in 100,000, and so on. Well, in the old picture of the universe without the accelerated expansion, if you wound the expansion backwards, then the whole of our visible universe had to emerge from a region that was so large that there was never time for light signals to pass from one side to the other. So it's a mystery as to how it became coordinated and similar. But with this accelerated interlude of history, it's possible to grow the entire visible universe from a region that's much, much smaller at past times. So small that there's easily enough time for light signals to go from one side to the other. And it's no longer a mystery why everything looks so similar from one direction to another and from one place to another. So that's what the acceleration does for you. It grows the entire visible universe from a region that's small enough to be coordinated. So this is all very nice. It was appreciated back in the early 1980s. But then very quickly, in 1983, at a meeting we went to in Cambridge, sponsored by the Nuffield Foundation, there was great interest in another feature of this model. And that was that this little patch here, our entire visible universe is the expanded image of this patch. It may have expanded much more than we could see today. But it can't be perfectly smooth. Quantum mechanics requires that there are always some tiny quantum statistical fluctuations. And we can calculate what they would be. And you could almost guess what they had to be, in fact, from the mathematics of the situation. And so all of a sudden, there was a remarkably different type of prediction, that graininess and fluctuation spectrum in this tiny patch would show up in the universe today. And we could hope to observe it and test whether these predictions were correct. So this gives you the possibility of explaining that number 1 in 10 to the 5. In practice, it's rather hard to agree that you can certainly do it easily, but you could fail to do it if you picked another model. What's more decisive is to predict what should the pattern be of the fluctuations on the sky from one scale to another. And that's something that we can observe in enormous detail. And there's been a succession of space missions to map the temperature profile of the universe in microwaves and to test the predictions of this theory, the simplest version of it. So here is a temperature map of the radiation on the sky, with the dark blue bits being above the average and the yellow and reddy bits being below. If you're a statistician and you look at this, the message you get is that this is a Gaussian random distribution. There are not enough extremes. A non-Gaussian distribution has lots of streams, lots of big, deep purple bits, and lots of pronounced red bits, and you don't see that here. So what you then do is to analyze the wealth of information in this and write literally hundreds and hundreds of research papers about the information that you can extract from this. And the simplest thing that you can do, you get the telescope to measure in that direction, measure temperature, and then maybe 5 degrees away, you measure the temperature again and compare. And then you measure every 5 degree separation over the whole sky. And then you average it. And you plot it on here, or you square it, and then you plot it on here. And you do that for every separation all over the sky. By going into space, you can do this over the entire sky and you're not hindered by the atmosphere. And you end up with this greeny picture here, and it's an interesting curve. So the green curve is a prediction of the simplest of these inflationary models, which has this surge of accelerated expansion early on. You don't need to know in detail really what the cause of the surge was, what type of particle. And the red points are the data points. And you can see that this is pretty impressive. The units here are trillions, 10 to the minus 12. Down here, there are uncertainties because you're looking at very large bits of the sky, and you can't pick very many of them independently. So the statistical errors become quite large. But as you get down here, you have all this detailed information. Here's the separation on the sky. It's about the size of the full moon here, ½ degree. And all the features in this picture, the height, the number of these little peaks, their relative sizes, they all contain information about the detailed structure of the universe at high precision. So there have been NASA missions of this sort. The most successful one currently, Planck, is a European mission. In the future, there will undoubtedly be another one. So if inflation hadn't occurred, if we hadn't had this surge early on, we wouldn't have this big peak here, like the ringing of a bell, fluctuations going away. We've just had a pretty uniform peakless distribution. So this type of data is one of the reasons why cosmologists take this idea of inflation, supposedly occurred when the universe is only 10 to the minus 35 of a second old, very seriously. Remarkably, you have very detailed access to information to test it. And just if you remember the general picture of this, why people are so interested in this precision is that if you change your detailed picture of the universe, suppose you don't know for sure how much material is in luminous visible form, how much is dark, all sorts of other properties of the universe. And so these little animations show what would happen if you changed your theory, the fraction of matter that was visible, and here you change the amount that was dark. Then what happens, you see in a general way, is that the shape of that picture, the spectrum on the previous slide, really changes quite a lot. The height of the peaks, the number of them, the relative heights here. So this gives you a picture of how much information you might extract from this data about all sorts of other things. So if you want to know the age of the universe, for example, you might well get a much more accurate answer by looking at this type of imagery than just doing radiocarbon dating or trying to date stars. So this is what I might call the sort of vanilla standard picture of inflation, and those observational successes, and the way it could tell you why the universe is isotropic and expanding critically and so on, is why people take it rather seriously. But then it turns out there are all sorts of other odd consequences of this theory that you probably need to take seriously or at least address because of the success of the rather simple model. We talked here about this tiny little patch here in orange, which is going to surge and inflate and eventually become larger than our whole visible universe today. But the universe may be infinite or a good deal bigger than our patch. So when that patch inflated, there will be all sorts of other parts of space all around it, with light signals passing across each of them individually. And they would inflate, maybe a different amount, starting at slightly different times. It's as though you have a foam of bubbles here, and you heat it up fairly randomly. And some of the bubbles will expand a lot, some just a little. Some may collapse and pop. So what this tells us is that we know we must live in a universe that's old enough for carbon and nitrogen and oxygen to form. And therefore it must be rather large in certain respect. So we could only expect ourselves to be inside one of these bubbles, one of these regions that was sufficiently big and old for that to happen. But if we could ever look beyond the boundary of our visible universe, this theory predicts that we should find the universe to be completely different in structure. Other regions would be of different density, different temperature. Internally, they may be rather smooth and have the same density, but we'd expect it to be different to the density of our patch. So there have always been philosophers, maybe theologians as well, who cautioned that you could never be sure that the universe was on the average or in detail the same beyond the horizon that we could see. But this was always regarded as a type of sort of overly positivistic skepticism. But for the first time, cosmologists now make a positive prediction that we should expect the universe to be locally rather coordinated and similar in structure, but globally to be far more complicated and completely different. Notice also, this whole universe might be very, very irregular and chaotic and peculiar here, in that properties are different from one coloured region to the other. After the inflation, we see things very smooth here. The irregularity hasn't been damped out and dissipated. It's been pushed where you can't see it. Once upon a time in the mid-1970s, before inflation came along, there was a very popular theory to try and explain how the universe became so smooth if it started in a chaotic fashion. And it's called chaotic cosmology, and the idea was that no matter how irregularly began, the irregularities would all get damped out by frictional processes and transport processes, so that if you waited long enough, it would look very smooth. One of the things I did as a graduate student was to show that this favourite theory at the time of Misner and others was impossible because of second law of thermodynamics, that the amount of entropy in the universe today placed a dramatic constraint on how much of that smoothing and dissipation could ever have occurred in the past. And the earlier you tried to do it, the more entropy you made. So there was really no scope for doing any significant dissipation and removal of irregularity by ordinary physical processes. Inflation gets around that by just pushing it beyond our horizon. It's still there, but we can't see it. Well, very soon, another idea was proposed. So you might regard this as making geography a much more complicated subject than when you were at school. Okay, geography of the universe, much more complicated than you ever thought. But unfortunately, history is more complicated as well. Because it turns out that if one of these little patches was to inflate, the way we talked about before, that it tends inevitably to create within itself the conditions for little parts of itself to inflate again. So it produces sort of two inflated offspring, as it were, or three inflated offspring in this picture, and then those offspring have little regions which inflate again. And the whole process is self-reproducing and appears to have no end. And so you might look backwards and say, well, need it have had a beginning? We see ourselves then as sitting in one of these inflated bubbles. And in the future, there will be other inflated regions. If we could see the entire infinite universe at one moment, we would see an infinite number of these regions. Some would be still inflating. Some would have completed their inflation. That's rather rare, in fact. And so an answer to a question like, did the universe have a beginning, suddenly has a more complicated answer. Our part of the universe that we see did have a beginning. It's a type of quantum beginning when this inflation began. And it's at a finite time in the past. But the whole network of this internal inflationary process, that's sometimes called the multiverse, need not have had a beginning. So you have two possible answers to the question as to whether the universe would have a beginning and whether it has an end. Our region might have an end. We'll see a little later that it doesn't appear that that's the case. It seems to be heading to expand forever. So this is the story that makes you think that history is rather more complicated than you ever imagined. And beyond our visible horizon, there is this huge geographical complexity and historical complexity as well. This is not something that cosmologists went exploring, and looking for. In some ways, it's regarded as a rather unsatisfactory state of affairs. You can never observe these other regions, okay? That's why they're other. But that doesn't mean that you can't falsify this theory. It would be possible, for example, for a particular theory, which predicted that there were all these other universe regions, to say that in every one of these regions you ought to observe a particular thing. The expansion had to behave in a certain way. And if we didn't observe that in our universe, that would falsify that theory. So you can falsify a theory of the multiverse without seeing any of the other regions. It's too much to ask that you would confirm the theory. Okay? That's true of any theory. So there's no reason why you couldn't falsify a particular version of this theory. You cannot falsify the multiverse scenario. That's impossible. But you can falsify a particular realization of it. One of the questions you might ask about this, this immediate thing you ask, well, we're in one of these regions and they all come out differently, maybe in some way. What's the probability of these regions having particular properties? So what's the probability of this region becoming big enough and old enough to make carbon and life? Are all these regions so fleeting and small that there's never any life? Well, sadly, I haven't got anything useful to report there. One of the great unsolved problems in mathematical cosmology is being able to work out the probability of any of the properties of these regions. It's a good general warning that if you ever read in a popular science book or a technical article a statement that the probability of something in the universe is high or low, that what's being said is probably nonsense, in the sense that we don't know how to predict the probability of anything in the universe. So we don't know the right probability measures. And every time you try to use simple probability, you tend to get infinite answers. So there's something that the universe and general relativity doesn't like about probability. And one has to think of a slightly different way of proceeding. What this picture of the universe changes for you, so when I was sort of younger as a student, there was a sort of overriding view that there was a theory of everything, of the sort that Einstein dreamed of discovering. That all the great things that you could see in the universe were somehow programmed into the initial conditions and the laws of nature. And Einstein believed there was one and only one possible theory of everything. And self-consistency alone could tell you what it was. One of the things that I argued about in the mid-1980s that wasn't very fashionable then, but sort of is now, anthropic principle, but this was not a likely view. That far more of the features of the universe than you might expect are not like laws of nature, they are like random outcomes, and they could have been different. And one of the things we want to know today is that what features of the universe are sort of programmed in by the laws and are inevitable, and which features, like the number of planets in the solar system, are just accidents, historical accidents, and could have fallen out differently. So which features arise through just random symmetry breaking, like balancing this pointer in a perfect vacuum and letting it fall. It'll go one way or the other with equal probability. What are the things in the universe that are manifestations of that sort of thing? And how do you work out the probabilities? And what do you do with them when you've got them? Because suppose you are able to work out the probability of having a universe that contains particular types of particle or star. What does that mean? What would you look at? The most probable outcome? Would you say, right, that's what we compare with observation? But then you think, well, what if the most probable type of universe is one that can't contain observers or life of any sort? Then we couldn't be in that universe, so we're not interested in the most probable one. We might be interested in the most probable one given that it allows observers and astronomers to exist. So the whole issue of both finding and interpreting probabilities is rather subtle. Well, let's close really by looking at a few things about the future of the universe. Okay, the universe is expanding today. Is it going to keep on expanding? What's the long-range forecast? Well, in some sense, this is a moot question. Other bad things happen long before the universe might come to an end. We've heard other speakers the other day mention the finiteness of the life of the sun. So the sun is about 4.6 billion years old. And it's in a phase of sort of gradual warming, but in about 5.5 billion years' time, there's a bad surprise. It's going to start running out of basic nuclear fuel of hydrogen that it likes to use, and it's going to swell up to produce this huge red giant structure. And the inner planets will be vaporized at that stage, so the Earth is unlikely to survive. Then it will implode and end up as a little dense structure called a white dwarf, about the size of the Earth, but the mass is 1 million times greater. And this will just cool and evaporate as eternity beckons. Here's a Hubble Space Telescope of this process happening elsewhere. In a star that looks more complicated, there may even be 2 stars here, that's why you've got the 2 explosions, or there's a magnetic field. So this sequence of events is common. You can see it happening elsewhere. So there is a violent end to the solar system. Life just has a finite interval to act out its play on Earth, at least. But our picture of the universe was changed in a very interesting way about 15, 16 years ago or so, when new theoretical ideas and new observational capabilities allowed us to map the expansion further out than ever before. And what was discovered was that when you looked far enough, the expansion appeared to be accelerating again. So it's as though this phenomenon of inflation was beginning again. And it had begun when the universe was about 3/4 of its present expanded extent. 3/4 its present size, if you like. So here's our picture we've seen many times. Here's the expansion. We're up here. But a little while ago, the universe starts to change gear and starts to accelerate. As far as we understand it, this is not a process of inflation like the inflation that occurred back near the beginning, but it may be produced by the same effects that created things here. So we don't really know. It's very fortunate that this began not too early in the recent history, as if it had been just a little bit earlier. Once it begins, you don't make any galaxies and you don't make any stars. So if stars and galaxies had not already formed before the acceleration began, they would never form. So the driving force for this acceleration is usually called dark energy, and it can have simple or complicated forms. And it's gravitationally repulsive, just like the stress that was driving inflation back here. And so when you analyze those maps of the universe's radiation structure that we showed the little movies of, one of the outputs that people focus upon is, if you want the most perfect agreement, what's the energy budget you need? And at the latest estimate, 68% or so of the total energy in the universe you want in this unusual form that's driving and accelerating the expansion. About 26.8% is forms of matter that are known as dark matter. So this is not matter that you and I are made of. Neutrino-like particles that it's hoped CERN will detect in the next few years in its next round of experiments. CERN is never going to shed much light on dark energy. Can't really detect this locally. Its effect grows with distance. And then there's the ordinary stuff that you and I are made of, atoms and molecules. A tiny trace element, really, in the whole show. But because it's luminous and spectacular, this trace element has guided people's intuitions and the making of stories about the sky and the constellations, and so on. One equation, as we're almost at the end. This acceleration, if we're physicists, And we look back at what Newton taught us. He taught us that there was an attractive force of gravitation, inverse square law, that falls with the square of the distance of the separation of two masses. So mass with value 1 and a star with value m. But there's another part to the gravitational force which Newton knew about, in fact, but chose to discard because he didn't think it was relevant for everyday purposes. But there's a second part which can be repulsive, and it increases with the separation. And Einstein's theory of general relativity introduced this as a possibility. So you could include it, or you could reject it. To reject it, you need a reason to reject it. And it were these astronomical discoveries at the end of the 20th century that revealed to the surprise, particularly the particle physicists, that this new constant of nature was not zero, that it was present and it dominated the dynamics of the universe when you looked far enough. And so this is the simplest version, if you like, of dark energy. It's this new constant of nature that people call the cosmological constant, or Einstein called the cosmical constant. And its numerical value in inverse centimetre squared is 10 to the minus 54. So it's the same units as miles per gallon. Okay. If it was just 10 times bigger, no stars, no galaxies. Biggest unsolved problem in fundamental physics is trying to explain this numerical value. Why does it have this value? Physicists know in a qualitative way what this almost certainly is. It's like the quantum vacuum energy of the universe. You can never have a completely evacuated space in quantum theory. There is always some so-called zero-point energy. And this is like the zero-point energy of the whole universe. So you're not surprised that it's present in a sense, but you have no idea why it's present with this very strange numerical value that means it takes over the entire universe in the relatively recent past. And people work very hard to try to explain this or come up with different theories that produce something like this as the driving force of the acceleration. So you heard some of them in the cookery demonstration last night. An interesting sort of subversive view to have about it is, you notice for your cosmologists, the particle physicists don't like the idea that they might not be able to explain something about the universe, that this might arise at random, and that this number might have no explanation. So this is a fundamental thing, so people are prejudiced to think that fundamental things must have fundamental explanations. But you must be careful. If you go back to 1600 and you were Kepler, then you would believe in symmetry as a guiding principle in the structure of nature. And you will be producing beautiful models of the solar system built on Platonic spheres and Platonic symmetries. If you were to suggest to Kepler that the number of planets in the solar system is just an accident, it doesn't have any deep explanation at all, this would have been anathema to him. But today, no planetary astrophysicist in their right mind would try to predict how many planets there are in the solar system. It's a complete accident of mergers and breakups and captures. It's just a historical accident. And so could it be in the future that some questions that we like to think of as being deeply fundamental, like the value of the cosmological constant, might end up being rather like the number of planets in the solar system? Doesn't mean that all questions are like that. There will be other questions that will have deeper answers. But we must be wary that some of them might just be historical accidents. And in different parts of the multiverse, the accident would have happened in different ways. Well, here's our accelerated expansion of the universe. We're sort of sitting here as it inflates early on, and then it decelerates, and then it starts to accelerate again. This acceleration of the universe introduces a new and deep and mysterious feature about the future of the universe. It ensures, when you look carefully, that the universe appears to be on a track to expand forever. It's not going to undergo a big crunch. But something rather remarkable happens in the future. We can think of our universe in a rather sort of onion skin fashion. There's a part of it that we've seen so far, okay, with our telescopes. There's a part that if we had a perfect telescope, we could in principle see that visible universe around us. And if the universe kept going, perhaps for longer and longer, we'd be able to see further and further and further. If there was no acceleration, you might continue to see further and further forever. But the acceleration means that there is actually, eventually, a fixed limit to how far you can see. It's like being inside a black hole. So one day, the stars and the external galaxies in the universe will gradually be passing out through this fixed horizon that will set up around us. And if there are cosmologists in the far, far future, 100 billion years to the future, eventually they will not see any external galaxies anymore. They won't be able to observe the expansion of the universe. They won't be able to deduce the existence of the dark energy that's responsible for that fixed horizon. So this is all that we would ultimately be able to see of our universe, which may be a good deal bigger. If there's a multiverse, of course, as we advertised, then things are bigger still. This limit to how far we might ultimately see introduces a final, unusual, perhaps dispiriting perspective. So astronomers in the far, far future will eventually not be able to do cosmology anymore. You won't be able to see distant galaxies. Also, remarkably, before that happens, and even before most of the long-lived stars die, you won't be able to observe that background radiation anymore. Its wavelength will grow so long because of the expansion that it won't be able to penetrate our galaxy's interstellar medium anymore. Physicists would say its wavelength is bigger than a plasma wavelength. And so it won't be able to get into the galaxy, we won't be able to see it. And its peak wavelength will be vastly bigger than we could observe. So these two core features of modern cosmology will not be available to observers in the future. And all the fossils from the very early universe will have been so changed and processed by local interactions, they won't be very good as clues to the distant past. The dark energy will not only be there, but it will become increasingly dominant, overwhelming everything else, but we won't be able to get evidence from far away of its existence. So if you're a cosmologist 100 billion years from now, it might be that the only way that you can learn about these features of the universe might be looking at old books or looking at journal articles in the distant past. So it's a sobering thought that our interval of cosmic history, which we've seen was conducive for the evolution and persistence of life, sits within a longer period of cosmic history, which is conducive to the study of the universe. So we're fortuitously situated in a long period of cosmic history where it's possible to gain evidence about the nature of the universe on its largest scales and at its earliest moments. That will not always be possible. Thank you.
Thank you so much for the excellent talk. Now we have plenty of time for discussion, and everything you have always wanted to ask about the universe and multiverse, now is the chance.
Thank you for the lecture. And, did I understand correctly that there would be possibility of starting a new universe from within our universe, like there would be in the visible universe?
It's possible in principle, but rather unlikely. the sort of thing that people have done, written papers about. See, this picture here, suppose we're sitting inside this region that's inflated. What we expect is that the amount of inflation will be vastly bigger than the size of our visible universe today. And so you would have to go a long, long, long way before you ran into the next different region. But you could ask, suppose that wasn't the case. Suppose the amount of inflation was just a little bit bigger than the distance that we could see. What would we see if we were running into this other expanded region nearby? So there would be big features in the background radiation in one direction. So people have tried to predict what they would be and then look to see whether you could argue there was any evidence for that. So in principle, there are effects of these other regions, but you would regard it as an extraordinary coincidence if just at the time when we're alive, the effects were just a little bigger than the distance that we could see. That was the extent of inflation. It will be an enormous coincidence. So the point that I was making was that in a scenario like this, you can hope to falsify some aspects of it, by more straightforward scientific methods, to be able to have direct interaction with other regions requires an enormously fortuitous, seemingly unlikely sequence of events.
So in that kind of very extreme state of events, there would be regions within our visible universe that have different kinds of physical laws happening there right now. And what we see would not be because of the same physical laws that we observe here and now.
Yeah, there are degrees of variation in this scenario. So you can imagine that these different bubbles, as it were here, beyond our horizon, they could be different in terms of their density and their temperature and things like that, but they might be different in terms of the strengths of some of the forces of nature, even the number of the forces of nature, or the mix of matter and antimatter. So there could be very big differences. So suppose this region was made entirely of what we call antimatter, and we ran into it. It would gradually destroy all the material in both the bubbles. So that's another version of this scenario, more extreme, where you argue that these different regions and different regions here would have different laws of physics, because aspects of the laws of physics also arise at random as it cools down. So that's a more extreme version, but it ought to have more consequences. But you can see that to do anything with it, you have to solve this problem of being able to work out what's the probability distribution, what's the likelihood of, say, a randomly chosen reason having 4 forces of nature at low energy, or 3 forces, or 2 forces, or even having 3 dimensions of space. So you have to be able to answer that question before you can make any progress with these more ambitious questions. Or you have to have some evidence that there is something very odd going on in our observations of that background radiation, which are consistent with interaction with the next bubble. And I think so far there would be no sort of consensus view that there's need to do that yet. But the more accurate your observations, of course, the smaller the effect that you can see.
If I get it correctly, the Higgs field theory that got a Nobel Prize almost 2 years ago states that there is a minimum level in empty space, level of energy in empty space. Now, when the universe expands and expands, the dark energy takes over, maybe even energy in matter is transformed into dark energy, I don't know. But what happens when the expansion has continued so far that all the energy in the universe is not enough to fill the minimum value of empty space? What will happen? Will we get a new constant, or will we get a phase transformation of some type?
No, I think nothing dramatic happens. So this cosmological constant term, which is envisaged to be, if you like, the vacuum energy of the universe, that certainly particle physicists and maybe some cosmologists long ago really expected was going to be zero. In fact, it's not quite zero. So as the expansion goes on, you're out of equilibrium. Everything is collisionless. You're not in a big interacting gas or sharing the same thermal state. So the cosmological constant itself, if that's the dark energy, is a constant value. It's driving everything farther and farther away. If you look at it in the right mathematical coordinates, it's actually static. So the quantum temperature is sort of staying constant. So it's not cooling in the way that you were envisaging. So it will arrive, if you like, at its vacuum state, and everything will be in that lowest temperature state, which is just given by the expansion rate. It's the same scenario, actually, as in some ways, as Bondi, Gold, and Hoyle's old steady-state universe. Steady-state universe is like the inflationary universe, but the inflation has no beginning and no end. The universe is always accelerating. So the great problem for it was how could you ever have any galaxies and stars, because any matter would immediately be accelerated. So it was hard to explain any structures. If Hoyle had thought in the right way, he could have predicted the spectrum of irregularities in the universe correctly. When I talked to him about this on occasions in the 1980s, I used to ask him, what was it about the steady-state theory that, was fatal to your mind? What was the biggest problem? Was it the discovery of the microwave background? No, he thought that could have been local at the time. It was the fact that this so-called continuous production of matter that sustained the model, he thought that it would have equal amounts of matter and antimatter. But the visible universe is not like that.
Can I actually continue on that by asking what is the role of observations in general in modern cosmology, or is there also a field of the study of possible universes?
Yeah, so, modern astronomy as a whole, cosmology in particular, has got three facets. So there's observational, there's what you might call mathematical or theoretical, but nowadays there's also computational. So, and some people are specialists at more than one of these. There are also people who build the instruments. Okay, rather technical people. Often when, if I talk to school children or something, they might ask, what do I have to know? What do I have to be like to be an astronomer or an astrophysicist? And I always say, well, there are so many different varieties. There are people who are very good at mathematics, there are people that are good with computers, there are people that can build things, that can build the detectors. There are people that can organize in huge collaborations. There are people that know how to interpret data, do statistics. There are people that know how to coordinate group projects on things. So these require people of very different personalities and skills. So there's not one type of astronomer. But what has happened, I think, in the last certainly 15, 20 years, there's been enormous advance in observational sensitivity. And this is brought about by CCD detectors, which received the Nobel Prize for Physics just a few years ago. So, before the 1970s, if you're an observational astronomer, like Hubble, you would be using photographic film. And photographic film is very inefficient. The best film was capturing only 1% of the light that fell on it. But when photometric detectors were brought into astronomy in the early 1970s, just using off-the-shelf technology in your video camera, that those detectors were sensitive to 50% of the light entering the detector. So just by clipping a relatively inexpensive CCD detector on the focal point of a big telescope, you increased its efficiency by a factor of 50. That would have meant building a telescope that had a diameter 7 times bigger, to go the old direction of just building bigger and bigger light gatherers. So quantum electronics is the reason for the revolution in astronomy. that we have detectors which in effect can detect single photons coming from astronomical sources. The satellite experiments exploit being above the atmosphere. The instruments on them are never as good as the instruments here and now, because the technology had to be frozen years ago when the mission was planned and launched. But if you have a detector at the South Pole today, it will be more sensitive than the Planck mission. It can only see a tiny bit of the sky, but it may be 10 times more sensitive. So it's this instrumental development that's going faster than theory, I think. There are big theoretical ideas, but we're in a period of great discovery in astrophysics. Extrasolar planets, comets, asteroids, and the link up with particle physics. We hope we will soon know what the dark matter is.
Well, thank you. These figures are so big, these billions and billions and things like that. And how would you look at, if you take a human being as this kind of starting point and say that we are about 2 meters tall, so then we can look at bigger things than we are and at smaller things than we are. Is there any use or help from looking at the cosmos if you want to investigate small things? You know, in chemistry you're going down all the time to nanometers. I don't know, there are very many Greek letters for going smaller and smaller and smaller. Is there anything to compare between diving very deep into something very small and going far with a rocket somehow to something very big?
Yeah, I think that there's a good way to look at these large numbers if you just sort of think from the point of view of doubling. So see this piece of paper. So, you know, I could offer you 20 euros if you could fold this in half 8 times. You know, you wouldn't be able to do it. But suppose I could cut it in half, okay, or double it in size. If I doubled this A4 paper, you know, to be A3, A2, A1, if I just doubled it 90 times, it would be the size of the whole visible universe. You know, it's a bit like the parable of the chessboard with the grains of wheat we heard the other day. So when you think in the language of doubling, the whole universe is not very far away. And then if you start halving the size of the paper, after about 112, 113 halvings, you're down to what physicists call the Planck scale, the smallest imaginable scale where the nature of space and time become quantum-like, and we don't really understand their nature. So, you know, just over 200 halvings and doublings of a single piece of paper takes you from the smallest imaginable scales in the universe up to the largest. If we were just cutting in half, you know, 40 times or something, I think you'll be down to the scale of the nucleus, and fewer halvings, you're down to the scale of an atom. So if you don't work on a linear scale, but you work on a doubling scale, then things become much more imaginable. You know, so it's easy to imagine doubling this paper 90 times. I mean, almost elusively so. But that's the size of the visible universe today, you know, 42 billion light years.
Can I ask about the visibility of the universe? Actually, we discussed this yesterday with you, but the fact that what is visible today, what is intriguing there is the fact that the further away we look, the older the information is. And in the sense that if we double that 90 times, in a way, what we see for far away, it's not there anymore, properly.
Yeah. So people often ask you, you know, you're talking about the universe when it's a fraction of a second old. You know, how can you know what the universe was like when it's a second old? In fact, conditions are quite moderate when the universe is a second old. You know, the density is sort of pretty much like this water. Conditions are not extreme. We know all the physics involved. If you keep going backwards, they become more extreme. But if you think about it, when we observe a distant galaxy, you know, maybe one in this picture here, you know, it may be billions of light years away. The light left billions of years ago. The galaxy might not be there anymore. So we always see the universe as it was long ago, not as it is. And there are some famous Hubble Space Telescope images which are really rather works of art, actually. Artists among you might be interested to explore. You know, these things like the Eagle Nebula. This really is it's like an artwork that's created with the help of the Hubble Space Telescope. You have to pick your area of sky, you have to pick all those color combinations and orientations that you want to make the image vivid. No one would see that when they looked out of a rocket ship or something. So it is an artistic representation of the data. But the Eagle Nebula is an interesting one because we now know that there is a shock wave heading towards it. The light left the nebula, you know, maybe 1,000 years ago or something, and in a few hundred years after it left, this blast wave will hit and destroy that part of the nebula. So it's no longer there. But people on Earth will have to wait another 300 or 400 years before they discover that. So you can calculate when it will have been annihilated. So this is an odd feature of the universe. It's the finiteness of the speed of light means that it takes time for us to receive information from the universe. And we are insulated from being affected by everything that happens in the universe all the time. If gravity and light propagated instantaneously, then we would be at the mercy of everything that happened in the universe all the time. We would be feeling gravitational shock waves and blasts of high-energy radiation instantaneously. But because it takes billions of years to get here, we are protected, as it were, from violent events in the universe. Newton's theory allows infinite forces, infinite velocities. The universe is not like that.
Thank you, Mr. Barrow. It was very fascinating to listen to you. My question is about communicating these things to public at large. Which are the things that are the most difficult ones to explain to people like us here today, or which are the things that are the hardest ones for us to take?
Well, there are some types of things where you think you know the words because the words stayed the same, but they're really different. So after Einstein, words like mass and time and energy had different meanings. So this is a rather subtle explanatory problem. Another problem with words of that sort is something like Hawking and Hart's, it's sometimes called the no boundary condition. That if you go far enough back into the universe in a particular theory, then time becomes another dimension of space. So you know what every word means in this sentence, but I don't believe it conveys any useful information to any ordinary person. So there's a type of deceptiveness of very simple language where you understand what every word means, but you don't actually understand what the sentence is saying. So, so one has to be a little careful that, you know, to make things as simple as possible, but no simpler. But as we've seen, there's a style of popularization that we've heard other people mention and use, which is of using analogy and metaphor. You know, so the universe is like a great clock, it's like a great computer. You know, a pulsar is like a lighthouse. In the 19th century, there was considerable sort of dispute about this way of thinking and representing the universe. It was regarded as a particularly English way of presenting things. And French scientists were completely against it. So, you know, they sort of poked fun at Lord Kelvin, saying, you know, or Maxwell, you know, you won't understand anything unless he can explain it as lots of little wheels and mechanisms and things. But they felt it was enough to have the mathematical description, that you didn't need these little pictures and analogies. And if you were a purist, you would say that mathematics is an analogy in a sense, but it's maybe the only analogy that doesn't break down. But people, certainly in the Anglo-Saxon tradition, like these little pictures. Okay, but that's a danger, because what physicists are always looking for, and astronomers, is a type of analogy. What you hope is that the really complicated thing that you can't understand at the moment, that if you only look at it in the right way, it's really the same as something else that you already understand. And therefore you can just import that other understanding, in theory, and use it to explain something else. And that's awfully tempting. So whenever you see it happening, you should be a little worried. So the Hawking and Hartle statement, time is another dimension of space, the fact that when you explore it a bit further, you don't actually understand what it means, may be a good sign. It's a way of looking at things that's not just a repackaging of something else.
It seems to me actually that we have amazingly had a cosmological thread in Abu Aqora this year, because we have had actually 3 different presentations on cosmology. So that's happened in a way by a coincidence, probably. But actually, you also referred to the black balloon as a metaphor or symbol. And it's still very difficult because universe is a balloon that doesn't have anything inside it, and nothing outside of it. So it's not a balloon in that sense. But on the other hand, it illustrates the fact that there's no center and no edge.
Yes. Other more complicated things can happen. The universe can have a funny topology, so it might not, if it's two-dimensional, it may not be, just like this flat surface here going on forever. It might be curled around, like a cylinder, and then curled around in the other direction like a sort of donut, ring donut. And this type of complexity is peculiar because everywhere actually it is flat. You might think this is curved, but it is not. So if you draw a little triangle on it, using the rule that you'll join 2 points by the shortest distance on the surface, and then add a third point, you'll find that you've drawn exactly the same triangle that you would draw on a flat surface. But if you draw on a curved surface, like a sphere or a wine glass, you will find that your triangle has curved sides if you take the shortest distance between 2 points on the spherical surface. So locally this is flat, although you think it's curved. So it has the same geometry as a flat surface locally, but globally it does not. And you'd like to know, does the universe perhaps have this type of weird topology? There are weirder ones than this. And the one that's rather hard to make, is the Möbius strip, where you join it like this, but you give it a twist. Locally, if you walk about on the Möbius strip, there are 2 sides, you would think. But if you explore globally, there is only one side. So the local structure of the universe may give you a misleading picture of what the global structure is. That's one of the main discoveries by mathematical cosmologists, really, in the second half of the 20th century, that the global structure of the universe can be extraordinarily elaborate and unusual. If we were just approaching a black hole, a big black hole, 1 billion times the mass of the sun, it's very benign. Its density is just the density of the air in this room, and you wouldn't notice anything odd if you entered it. You would if you tried to get out. You wouldn't ever be able to reverse your path. But as you entered the black hole, you wouldn't feel any exotic, strong forces or anything like that. So locally, everything seems fine. But globally, if you try to leave the black hole with your, super fast rocket, you would never be able to do it. And you would discover that there was something very mysterious about the space you were in when you looked globally. So locally, everything is simple. Globally, can be extraordinarily complicated. The multiverse is a big, big example of this. You know, you might be looking locally, like in this room, in one part of one universe in the multiverse. Locally, it looks rather simple, floor pattern. But globally, it's unimaginably complex if there really is a multiverse. So you have to be very wary of extrapolating topologically from local conditions to global ones. And also, I think, be wary of the prejudice that every question you can ask about the universe can be answered. If that were true, it would be an extraordinarily anti-Copernican state of affairs. Why should all our questions be answered? You know, the universe is not fashioned for our convenience. And so we shouldn't be surprised that, you know, we're never going to know if the universe had a beginning, or whether it's infinite, or whether it's finite. Because we could only observe this particular finite region, the visible universe. There are other questions that we'll discover in the future that we can answer, questions that we haven't really conceived of yet.
You said that the end of the visible universe is in light years, roughly the same amount as the age of the universe? Did I get that right?
No, I said 100 billion light years, 100 billion years to the future will be when this sort of horizon, this surface beyond which we can't see, will be fully formed and it will come in sort of nearest. At present, it's a long, long way away, further than that. But as the dark energy becomes more dominant, it'll be established closer and closer. So a rough way to think about it is, you know, we're thinking of our visible universe, the place that light reaches us from. And if the universe is accelerating, it becomes harder and harder for light to reach us. And in fact, eventually it becomes impossible for it to get here from beyond a particular distance. And that's the distance which we can't see beyond.
Thank you for your presentation. You might have already answered my question, but I would like to know what's the difference between dark energy and dark matter, or I think you said that dark energy accelerates expansion. So what does dark matter do, or does it do anything?
Dark matter's the name that people have used for a long time just to describe a material that's not luminous. We know it exists because if we look in galaxies and study the motion of stars in galaxies, they move as though they're feeling the gravitational field of about 10 times more mass than is shining in the dark. So you can tell how much material is around by measuring the speed of luminous stars. And if the dark forms of matter were not present, the galaxies would have just dispersed. There's not enough gravitating mass to hold them together. So everywhere you look, then you look at clusters of galaxies and you can infer how fast the galaxies are moving around. And you find the same type of answer. We need 10 times as much material in a dark form that we're not seeing as in a bright shining in the dark form. So this is what people call dark matter. And your first idea, as people in the 19th century thought about, was, well, how do we know it's just not rocks? You know, stars are rather unusual things. They're just the places where the density of matter in the universe got so high that nuclear reactions could begin. So that's rather extreme. So you wouldn't be surprised that there's loads of rocks and asteroids and planets and stuff and gas, you know, that's not luminous. But you then start to look at the consequences of explaining all this missing stuff you need to explain the motion of the stars by just dark forms of you and me and ordinary bits of matter. And it turns out that if you did this, certain nuclear reactions in the history of the universe would go much, much faster because there would be more nuclei to take part in them. And the amount of the very lightest elements of deuterium, helium-3 that we see would not be present. in the relatively large abundances we see. They would all be destroyed. So there's this indirect reason for believing that all this dark material can't just be ordinary types of matter, atoms and nuclei, that it must be something that doesn't take part in nuclear reactions. And so that gives you one or two options. Particles like neutrinos, which are a source of radioactivity, so they don't take part in nuclear reactions. One or two other funny things like black holes, tiny black holes. They're not elementary particles at all. So, and then you start to look with large computer simulations, what happens if you fill up your galaxy with all these different sorts of dark matter? And some of them make the luminous matter organize itself in the wrong way. You know, they become too condensed in the centers. And other forms cluster in the right way. And the best candidates are not the neutrinos that we know, but new types of neutrino, which we haven't had the energy to produce yet in our accelerator experiments. And so these would be neutrinos with masses 20, 50 or more times the mass of a hydrogen atom. And CERN currently has ranked up its energy, and it hopes in the next year or two to start gaining some evidence for the existence of these new types of neutrino-like particles. So it's got high enough energy, it hopes to make them for the first time. And it's these particles that sometimes they're called cold dark matter. Cold just means they move very slowly, low energy. So when the molecules in the room move more slowly, the temperature goes down, it's cold. If it was hot dark matter, it would be very lightweight neutrinos that move very quickly. But they don't seem to be a good idea. So dark matter is this stuff that we hope our experiments will identify for us. So this is a soluble problem. I mean, it may be that none of these particles are found at CERN, and you have to think again. Dark energy is completely different. That's matter with this repulsive gravitational force. Discovery of dark energy, expansion of the universe, confirms that this type of energy exists in the universe. So what we wanted for inflation does exist. And the Higgs particle is an example. But it's not, the Higgs particle is not the one that produces inflation. It's not really heavy enough. So this is an unknown form of energy. You shouldn't really think of it as being particles. It's a field of energy, like a field of force. And its effects are the same everywhere. It doesn't cluster. And its effects get bigger on bigger and bigger scales. So this is weird. Most forces in nature, the effects get bigger when you go in smaller and smaller scales. So we don't really know what this is in detail. You're sort of narrowing down how it behaves and how to describe it. But why does it have the strength that it does? Why did it come into play when it did? We don't know the answer to those questions. So dark energy is dramatic and hard to understand, difficult. Dark energy is all over the place, and we can measure its effects, we can study it in some detail, and we hope that we might detect what it is very soon. The reason we think it's this 10 to 50 or so times heavier than hydrogen type of neutrino is because you can actually calculate what should be the abundance of these sorts of particles in the universe from the early stages. And particles with those masses have just the right abundance to explain the amount of dark matter. So there's a sort of circle that's closing. If you detected this particle, you could check precisely if you had predicted the correct abundance by comparing it with how much you needed in nearby galaxy or our own galaxy. These particles are really very weakly interacting. So there's millions of dark matter neutrinos going through your head at this moment. They're moving around this room about 250 kilometers per second. And there's a few hundred of them, about 400 of them in every sort of cubic centimetre of space. So they interact very weakly. You don't feel any ill effects.
Well, perhaps since the dark energy is going through our heads, it's time to stop this session. But anyway, I suggest we give a big hand to John Barrow for the excellent presentation.
Thank you.